Please welcome Marian Gazdik, GeForce.
MatNex. I would like to say a few words about MatNex and what they're doing. We live in an era where we see in real life AI change the software world forever. It's now coming to robotics. And the next is going to be materials. Because materials is where the most profound impact on the planet can be made, because 50% of global greenhouse gas emissions are coming from producing materials. MatNex is redefining materials discovery using AI and quantum modeling to compress what once took decades in R&D into just months. They create carbon-neutral alloys, semiconductors, and catalysts that can reshape energy, aerospace, and manufacturing. That's why we see them not just as a startup, but as a scientific revolution. And that's why we nominated MatNex for the Science Breakthrough of the Year.
Breaking the wall of conventional materials discovery, Richard Tomsett, MatNex.
Thank you. So every new technological advance relies on materials, but materials have become the bottleneck to the next generation of technologies. 52% of critical materials are already at risk, and developing replacements is painfully slow and expensive. That's because it relies on experimental trial and error to find new materials. That means it can take over $100 million and over 10 years to take just one new material from concept to market. That's the problem that we're solving at MatNex. To understand why it's so slow to find new materials by trial and error, imagine that you're looking at a casino slot machine, but instead of trying to find a winning combination of lemons or horseshoes, you're searching the entire periodic table for a winning material. Now, even if we only look at materials containing 4 different elements, as I'm showing here, and we limit ourselves to steps of 1% changes in the amount of each element in that material, we're going to see 7 quadrillion possible combinations of materials, which we're now spinning through in our materials slot machine. And we're now going at 10 materials every second. But you can see that the search bar that I made lovingly at the top there is not moving. I don't know why I bothered. We're stuck at 0.0000% progress. And if we wanted to get to 0.0001% progress, we'd be here until Christmas, 2027. So the scale of the challenge is staggering, but it's also an incredible opportunity, because hidden in those quadrillions are materials that could revolutionize clean energy, manufacturing, and computing, if we can find them. And that's where MatNex's AI comes in. So what you're seeing now is a public data set of known materials as viewed by MatNex's AI. Similar materials cluster together to form islands of similarity, and the dark spaces in between are the vast unknown. And conventional research would stay stuck to these islands as scientists painstakingly build on prior knowledge through trial and error. We could randomize our search a bit further, exploring the unknown, exploring more of the space of the unknown, but you're vanishingly unlikely. It's impossible to actually land on a useful material this way by chance. So at MatNex, we solved that problem by developing AI to search this space intelligently. So what you're now seeing, the green dots now appearing, are materials predicted by MatNex's AI. And you can see them filling in the gaps in the space and connecting together the islands of known materials. So it's searching the unknown, but it's doing so intelligently, guided by physics and by prior knowledge. This intelligent search can generate thousands of likely candidate materials in just a few days. And then we need to test those materials in the lab to check the AI's predictions. To prioritize these tests, we first simulate the properties of the materials, and we only move forward to the lab those with the best performance. And this is where AI comes in again. We use AI models to run simulations 10,000 times faster than the equivalent quantum mechanics calculations. This speed means that high throughput screening becomes possible, moving discovery times from years down to months. We bring this together in our MatNex suite of tools. We start with our models in our toolset that generate and manage the candidate materials. And then our MatNex AI models rapidly screen and simulate those materials. The most promising ones move on to the lab, where we make and test them. And successful discoveries then become new products, forming a portfolio of discoveries that can power the next generation of technologies. And this isn't just theory. We've done this in practice with rare earth element-free magnets. We set a search up to work with 3 different objectives: minimizing cost, eliminating the rare earth elements, but also maximizing the magnetic hardness of those magnets. We generated tens of thousands of candidates per week, screened those down to 70 promising candidates that we then synthesized, and we could confirm that the properties of those candidates matched what was predicted by the AI. I'm running out of time, so I'll just say we've got a lot of traction. We've won $14 million of venture funding and $1.5 million of grants. We've signed 3-year agreements worth $70 million with our customers for our new materials. So we're not just imagining the future of materials, we're building it here today.
Not bad. You made it in time. If you like to put your microphone a little bit further,
apologies,
more comfortable. No, don't worry. Okay, we have a lot of questions. 1, 2, 3 to start with. Please.
So I think it's a super promising technology, very interesting. But there are quite a few companies doing that. Google, for example, was one of the first putting that to work. So what differentiates your company from the other?
Yeah, that's a very good question. There's a lot of great companies in this area. There are 2 things really that we think distinguish us. The first is that we can generate all of our own data from first principles, whereas other companies have to buy in their data. And we have the largest materials-focused supercomputing capability in the world to be able to do that. And the second thing is that we focus on actual synthesizability of the materials as like a key, as a North Star for everything we do. So we make sure that the materials we developed are genuinely synthesizable and not just theory.
Luca, you're the next.
So is the business model like I come to you and I ask, make me an alternative to indium tin oxide, and you tell me the composition? Is this what you sell?
It's something like that, yeah. So it's you can think of us as sort of, I guess, the NVIDIA of materials, where that's the plan, where we generate the IP through our AI models developing the compositions and the synthesis processes. And then we would license those out via patents to companies who are interested in making those.
Mm-hmm. Next one will be Inga.
So actually, I had a similar question. Do you already have customers?
We do already have customers, yes.
You can name it? No.
I can't name them specifically, but I can tell you that we're working in the hard magnets area, magnetocalorics, and various other areas. So there's a general purpose technology. We're not just focused on magnets, we're also working towards semiconductors and other materials.
Cyriac, is it a question or a comment?
Question.
Okay.
So AI lives off of validation in real life, and I understand how fast the search part is, but how fast is the validation part, and how scalable is that validation part?
Yeah, that's a great question. So one thing that we're really working hard towards, and this is one of our kind of key areas of focus at the moment, is making sure that once we've made a prediction with our AI systems and our simulations, the lab experiments they have to do genuinely are very likely to work. So last year, we went from an example from 11 million predicted candidates, 8,000 of those we screened down to be novel. 70 of them ended up being made, as you saw in the example, which I didn't quite have time to go into. And then 2 of those were actually useful. This year, we've made some advances in AI that means that our search is 4 times more efficient. So we're 4 times more likely at the end of that search to get a candidate that we can actually make. So it's all about making our predictions more reliable so that when the people in the lab take it, their experiments are more likely to work.
We still have 1 minute. Another question? Yes, please. First row.
Can you get more concrete? What's your first product application? Give me one.
There's the rare earth element-free magnets is one key area. So that's replacing magnets in things like wind turbines, electric vehicles, etc. Another area is magnetocalorics, which is magnets used for efficient refrigeration. We're also currently looking sort of at the superconductors and semiconductors areas.
Thank you.
Milena, last question, 27
The business model, are you testing to have partners to do the validation faster?
Very fast, please.
Possibly. At the moment, we're doing it
Avatar.
in-house, but possibly, yeah.
Okay, great. I think for 11 seconds we won't make another question. Sorry, it's too short. I'm very sorry for that.
You could do a yes/no answer. Yes.
Yes, I mean, we still have networking afterwards. You can ask further questions. Thank you very much.